Welcome back to Finite Element Methods, Math 574 here at the University of Tennessee. This is class number 19. And we've been talking about what? So we've been talking about the diffusion problem, which is it's a parabolic problem. And this is different from the elliptical problems that we've been the elliptic problems that we've been studying up to now, because this one is a problem where the solution has as its independent variables both space and time. And so the problem manifests itself with both partial derivatives in time and space. And so we gave the equations last time and the time before, and we talked about the energy estimates that you get for the weak solutions of the diffusion problem. And we also talked about the semi-discrete Galerkin approximation of the problem. And now in this class, we want to drill down a little bit further and look at some properties of that semi-discrete Galerkin approximation. And then the next thing after that is to look at a fully discrete approximation and start to investigate some properties of that. So without further ado, I'll start by reminding you what the discrete Galerkin approximation for the standard diffusion problem looks like. So after we've converted from the finite element formulation of the problem over to coordinate formulation of the problem, we get this matrix, this system of ordinary differential equations involving matrices. The matrices that are important here are the mass matrix and the stiffness matrix. The stiffness matrix is exactly the same as it was before. So that is given by, or gotten by, or I should say its components are calculated by inputting the basis components, or the components of the standard finite element basis, into the A bilinear form. The mass matrix is similar. We take basis elements, or elements from the basis, the so-called hat functions, if you want to think about them that way, and we put them into not the A bilinear form, but we put them into the standard L2 inner product, and we calculate the elements of that matrix that way. So the definitions are given in the last set of slides, and so I won't go through those again. But the mass matrix sits in front of this u vector. Of course, this is the time derivative u, and A multiplies, the stiffness matrix multiplies the vector u of unknowns. This is equal to the sum of these two operators is equal to a given forcing function, f. And so actually this is the coordinates of the forcing function once we've gone from finite element functions, or in this case, L2 functions, over to coordinate space. The initial conditions are expressed this way. All right, so the first thing I want to say is we're not stuck with this coefficient matrix in front of the u prime. We can get rid of it or multiply through by its inverse, because that matrix is invertible. In fact, the mass matrix is SPD. So the mass matrix, again, I guess I could have just pointed to this this definition for what it was. It's equal to its components, of course, as usual, where the components are phi j, phi I in the L2 inner product. That's how I calculate the components gij. So this matrix is SPD. That's what we want to prove. How do we do this? Well, what I'd like to show is that an arbitrary expression like this, u transpose gu, is greater than or equal to 0, and only equal to 0 if u is itself equal to 0. So that's what I want to prove. Now let's see how this is done. So let UH be an arbitrary finite element function. any arbitrary finite element function. Now, this is only a spatial function, it's not time dependent. Any finite element function can be written as a linear combination of the basis vectors. These coefficients here give me what are known as the coordinates of that finite element function with respect to a certain basis. The basis that I'm going to use is the standard basis B. Now, I say that this is the finite element function connected to its coordinate vector. In fact, what I mean here is that this finite element function has a unique coordinate vector, and there's a one-to-one mapping between finite element functions and vectors in this space R and R. And the way that these are created or realized is that this vector has these coefficients, which are the coefficients in the basis expansion. That's where this derives from. Now I could go one way or the other. I can go from the finite element function through the basis to the coordinate vector, or I can go from the coordinate vector through the basis back to the finite element function. You see there's a one-to-one correspondence of these objects. And in the case I'm going to let this or this, however you want to think about it, be arbitrary. Then I'm going to make this bilinear form here. U transpose GU. Well, what is that? This is exactly the same as, in fact, I could write it a couple of different ways, but this is just through the definition of the dot product, is just UI times the ith component of GU, sum from I equals 1 to NR. So that's just the definition of the dot product. Now I can break this guy, this ith component of this matrix vector product, into its components. So I write that as sum from j equals 1 to nr, ui, actually not ui, but gij times uj. That gives me this ith component. And I can move this guy in or out of this sum as I please. Can take it in, take it out, doesn't matter. And then I just realized, well, writing this UH in its basis expansion, this expression here is exactly the same as this expression here. So I've got equality all the way down to here. If you don't see that now, take a sheet of scratch paper out and convince yourself that that's how it works. Now, from this point, I notice this is just the L2 norm squared, right? The L2 norm of UH squared. And so that's a number which is greater than or equal to 0. Right, so that's one part of the SPD that I want to prove. Obviously, G, through this definition, is a symmetric matrix. I'm now moving on directly to proving that it's SPD. This is not exactly SPD. This is what we call symmetric positive semi-definiteness. To make it positive definite, not just semi-definite, I have to show that the only way that 0 can be achieved is whenever u is exactly equal to 0. It's clear from this statement here that the only way I'm going to get 0 is when UH is the 0 finite element function. But remember I said there's a one-to-one correspondence between these functions. The only way I'm going to get 0 for the finite element function is if I have 0 for the coordinate vector. And so that proves that G is symmetric positive definite. So that means back up in my original formulation, I can just multiply by G inverse here. That gives me the identity. Multiply by G inverse here. That gives me some new matrix. You can call it B if you want. And then I'm going to multiply G inverse to this vector. This is a known forcing vector in time. And so that just gives me a new vector. So I can basically undo the fact that G is in this position if I wanted to. And that's exactly what I've written here. I've just multiplied in this formulation through by G inverse on the left, and that gets rid of the coefficient matrix G that was there. My initial conditions change or can be changed by a similar sort of methodology, just multiplying both left and right hand side by G inverse gets me this new initial condition. Of course, this system is entirely equivalent to the one I had before. Now, whether you look at this system or the previous one, we can apply the standard theory of linear finite element or of linear ordinary differential equations. And it's very clear that this system of ordinary differential equations, linear ordinary differential equations, has a unique solution on the time interval 0 to t, as long as f is a sufficiently nice forcing function on that interval. And so I won't go into all the details of what sufficiently nice is. That's for your ODE course, but it's not hard to figure out what f should be for this solution to exist for all t up to some capital T. Now, in fact, if we know that f is sufficiently nice for all t period, for all t greater than or equal to 0, then we have a solution for all time. But in any case, we're always going to suppose that f has that sufficiently nice initial data, and we'll always be able to assume that we have a solution. Now, we have this semi-discrete method. I want to show that the semi-discrete method is actually stable. Now, I could either write it using this ODE formulation that I have here, or now we have an equivalent formulation here. But I'm going to go back to my original statement of the method before I converted to a vector equation. And this is useful because showing that the semi-discrete Galerkin approximation is stable is a lot easier from this point of view. So just to remind you, the semi-discrete Galerkin approximation for the diffusion problem is to find a UH that, and the way I think about UH is a little bit special and different. I think about it as a mapping from the time interval 0 to t into this spatial finite element set. Okay, this is a finite dimensional space, actually a finite dimensional Hilbert space. So UH is thought of as a mapping from the time interval to the finite element space. So that if you give me a time, I'm going to give you a finite element function. I'm going to look for U of that type that satisfies this equation, this weak formulation equation, UH prime inner product against psi plus A bilinear form UH psi equals the L2 inner product of F against psi. Where psi, what is that? That's any finite element function that you want to choose. It's arbitrary. This has to hold for all time between 0 and t. And then finally, the initial conditions should be satisfied. And the initial conditions are UH at t equals 0 should be some projection of our finite element function or our initial data v into the finite element space. So what projection this is quite yet, I'm not going to say. It could be what's called an L2 projection. It could be what's called a Ritz projection. It could even be the interpolant. Okay, so the only projection operator that we've really looked at so far is what we call the interpolant. So that's a good enough one to use there, at least to start. So you can think about it like this. V is a smooth function, maybe H01 function, and I take its interpolant, and that moves it from the C infinite or infinite dimensional space of functions into the finite element space. All right, so let's start by supposing that for all h greater than 0, VH L2 norm squared is less than the L2 norm squared of the original V, plus some constant, which is like an error factor. So this also could be, there's another way that this is commonly done, and we could assume that in the L2 norm, this projection is less than the L2 norm of the original function. This is also a standard possibility. But this is what we call a stability statement, okay? What we're saying is that our projection in the L2 norm is not bigger than a constant plus the original the original norm squared, or the norm squared of the original function. So this is like a stability statement. This statement is a more common and more powerful stability statement. All right. Let's see. Can I get this one from that? Yeah. So this one, I can get this one from this one just by supposing that, well, C is actually just equal to 0. So let's encode that and make sure that that's allowed. So I'm going to change this and say for some constant which is greater than or equal to 0. Okay. Now that constant has to be independent of h, because as I take h smaller and smaller, I don't want that constant to change. So everything over here is independent of h. Everything over here, well, this can have a dependence on h, but hopefully it doesn't get worse as h gets smaller and smaller. And this estimate prevents it from getting worse. And so we call this a stability estimate. Well, if v and vh satisfy that, then the semi-discrete approximation is stable in the following sense. I can show that the maximum over the time interval 0 to t of this norm squared, L2 norm squared of UH, is less than some constant C0, which is entirely independent of H. In fact, I know what that constant should be. It should be the L2 norm squared plus a constant times this norm of F squared. This is the L2 norm squared of F, plus that same constant that appeared here. Okay, so that's what that is. And we can show this norm, or this is norm squared actually, of UH, the finite element solution, is less than that same constant. So I'm going to prove these two stabilities. Now, what I notice about these two stabilities is they're exactly the same stabilities that I got previously for the weak solutions. The only difference is I didn't have this constant. Okay, so these are the same as before, but I don't have this. Okay, that's the only difference. But these are otherwise called energy stabilities, because we think about the energy being this object here, or let's say that, and this object is being reduced at every time I can show. We'll talk about that a little bit later when we talk about the fully discrete methodology. All right, so what we're going to do is we're going to use this formulation of the problem to prove those stabilities. How do we do that? Notice that this test function can be anything from VH. So whatever I put in there should be from VH. That's an important point. So what do we want to pick? Well, UH is a perfectly good function in VH. So let's use psi equals UH. If I do that, insert, then I get this equation, right? Well, I can first notice that this guy here, this term here, is pretty nice. It's just 1/2 times the time derivative of the L2 norm squared of UH. Okay, so how do I show that? Well, this is just an integral. This is an L2 integral, and notice that I'm going to do. If you don't see anything on these bilinear forms, then you can always just assume that it's the L2 bilinear form, or the L2 inner product. This is just an integral, and so I have a derivative with respect to time inside the integral, and so I can just observe that if I take the time derivative of an integral like that, it's an integral what? It's a spatial integral. Time derivative of a spatial integral, and it's UH t dot u, well, don't need the dot, UHT. Just take that time derivative and see what you get. What I claim it's a spatial integral. So if I do that, then what I get is a term which looks like this, only twice as large. So if it's twice as large, then to make it Let's make it half as large by multiplying by a half. So if I do this calculation, you'll notice that I get this term here. So that's where that comes from. This is just, we observe, just the L2 norm of that function squared. So that explains that term. What about the second term? The second term is exactly what I want already, and I don't need to modify it. As is the third, I don't need to do any modifications of this term. Now, how am I going to finish this estimate or complete it? Let's take the Cauchy-Schwarz inequality of that. So that gives me an F norm and the L2 norm of UH, the second term, just using Cauchy-Schwarz. Well, I want to balance this term with this term, or what I really want to do is hide this term. This is called hiding the term. Hide this term and this term. How do I do that? Well, I need to boost this to an H1 semi-norm. The way to do that is to use a Poincare inequality. So Poincare gives me Poincare constant and times UHT H1 semi-norm. So don't be fooled. This is, so normally when we apply the Poisson, or sorry, not Poisson, but the Poincare inequality, when we normally apply it, there's no time dependence on a function. But we're just applying it at every fixed time. And if we do that, then L2 norm, spatial norm of UH is going to be bounded by the H1 semi-norm of UH. Okay, so this is the Poincare constant. Now I'm going to use the algebraic geometric mean inequality the same way I did last time, so I'm not going to explain it. It's the same. And what I want to do is arrange things so that I get a 1/2 on this term, and this should be squared. So typo, there we go. That should be squared once I do that. All right, so go back and look at the algebraic geometric mean inequality if you want to see how that is done. So I just want a half here, and I want, if I want the half there, then I have to penalize this term a little bit more to get that half. Why do I want the half? It's because I want it because I can hide that term in this term over here. And the way I hide it is I'm going to subtract both sides, the left and the right, with this common term. And if I subtract that common term, then the direction of inequalities doesn't change. When I subtract it, it goes away from here. And over here, I'm going to get a half times UHT H1 semi-norm squared. But now I have a half in front of this term, a half here, and a half in front of that. And I'm simply going to multiply through by 2 to get rid of it. So that's how I get that term. Next, I'm going to integrate this term from t equals 0 to t equals some arbitrary s. If I do that, this is a perfect derivative. This is an absolutely perfect derivative. So if I integrate a perfect derivative, I can just use fundamental theorem of calculus to get that the integral is the antiderivative of this perfect derivative, which is just this function itself, evaluated at the endpoints t equals 0 and t equals s. So t equals s minus t equals 0. Why is this t equals 0? Well, it's going to be UH evaluated at time 0, but that's just equal to my initial condition, VH. This integral here, by the way, I don't have to integrate from t equals 0 to t equals s. I could integrate from one lesser time to some greater time, like t1 to t2. So we'll do that a little bit later. But in any case, if I integrate from t0 to ts, the 0 term comes out to just be the initial condition, and then I have an arbitrary term otherwise. Now this term that existed on the right-hand side, what am I doing? I'm integrating every term, okay? This guy gives me an integral 0 to s, and I'm going to take that s all the way up to its maximum value, which in this case is the value capital T. So this guy, the reason why I like this one is because it's completely independent of s. I don't have to worry about any s dependence there. After doing that, next I'm going to take this and move it to the right-hand side. And then I'm going to estimate that term. Instead of VH, I'm going to estimate it so that I can replace VH by V, or actually the norm of V squared plus a constant. So that's why I'm getting, instead of VH over here, I'm getting V L2 norm squared plus a constant. All right. Now, sometimes I don't need that constant. There's a certain projection that you can use where that constant just goes away, but otherwise it's just going to be there. Let's see. What's next? Next, I'm not going to go through all the details, but basically I can estimate this from below by UH L2 norm squared. And then I can take the maximum of that term in S, can take it to be the maximum possible value it achieves, varying S between 0 and capital T. This term over here is completely independent of S. It acts as an upper bound. So that says that the maximum of this is less than this. And that's the first estimate that I wanted to prove. Well, what do I do about the second estimate that I wanted to prove? That one's a lot easier. All I have to do is realize that now this is completely independent of T on this side, so I can run this upper bound from an arbitrary value S up to the fixed upper bound, capital T. And so I can do that because even though this is increasing, even though that's increasing as S gets larger and larger, it's not going to increase unboundedly. It's bounded above by this term, which is completely independent of S, right? So that's how I achieve the first and the second bounds. All right, so that says that what? That says that my semi-discrete approximation satisfies exactly the same stabilities as my original PDE problem, the original diffusion problem. That's quite nice. Now, I don't have to integrate from 0 to S. I could integrate instead from T1 to T2, as I explained down here. And so if I set F equal to 0 in particular, okay, let's see, let's make it more explicitly 0. If F is identically 0, then what do I get from the above analysis? Well, up to this point, everything is exactly the same. It's just I don't have this term at all. Okay. I integrate, and this term is not there. This term is not there. And so I'm not going to integrate from 0 to S anymore. I'm going to integrate from T1 to T2. So this difference here is U at T2 minus U at T1. Okay. And from there, I can show that, well, since F is completely 0, then what I can prove is that this function is a decreasing function. That is, if at some later time t2 I evaluate this function, I get a lesser value than if I had evaluated at t1. And of course, this is just going to be like t equals 0, which I could choose. That value is bigger than the value at t1, which is bigger than the value at t2. And if I take another greater value greater than t2, then it gets smaller and smaller. So what this is saying is that this energy here is decreasing over time. So the picture is, if I track the L2 norm of the solution, L2 norm of the solution as a function of time is, that one doesn't quite work. I want to describe a function which is actually decreasing. Something like that. The L2 norm decreases over time, so that if I take any T1 and any T2, T2 being the later time, and I examine the values at those two, I see that the value at T2 is always lower than the value at T1. Okay, so this is a type of stability, and it follows very quickly from the analysis that I have above, And all I'm going to do to change it, to make it not exactly like the analysis above, is instead of integrating from t equals 0 to t equals s, I'm going to integrate from t equals t1 to t2. Very easy. All right, now to finish, well, to continue this discussion along, I guess, I want to come up with a fully discrete, completely realizable numerical method. That is something I can actually put in a computer and compute and get approximations for my solution. But we have to think about what might be fair to do, what kind of approximations might be fair. So it turns out we're not going to do the finite element method in space. We're not going to do the finite element method in time like we've done space. It just won't work out that way. There's a much simpler idea that will work, and that is instead of, so basically it goes back to the weak formulation of the semi-discrete problem, this guy here. And what's the bottleneck here? Well, the problem is that I have what makes this not an algebraic equation, but an ODE algebraic manipulation, is I have this time derivative. Well, so what I might do then is instead of working with that time derivative, let's use the difference quotient. The difference quotient is an approximation of that time derivative. So this one is in particular an Euler approximation because we're using this first order approximation. Now, is it backward Euler or forward Euler? This one is going to be backward Euler because we're going to make it implicit. Okay. So it's a backward Euler method. Now this S is equal to t over some positive integer k. Okay, so this is the number of time steps that I want to take. This is the final time. And if I want to figure out the step size that I need to get or need to have, then this is going to be t over k. Okay, and this k is some positive integer. Then what we're going to be looking for is a sequence of finite element functions, some sequence of snapshots, u1h, u2h, u3h, up to an arbitrary one, uhk, little k, this is little k. And then if we continue along, then we end with UH capital K. That's the last approximation. So what I've effectively done here is I've taken my time interval and I've broken it up into a number of smaller pieces. So if this is capital T, this would be S equals capital T over, I think I did 8 intervals there. Let me count. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. All right. So this is T1, T2, T3, T4, T5, T6, T7, T8. All right. And T's are defined down below. Tk is just equal to S times little k. Right? So T1 is just going to be S. This is 2 times S, 3 times S, 4 times S, 5, 6, 7, and 8 times S. Right. Okay, so that seems to be fine. What else do we need? So what I've done is I've replaced the time derivative by this time difference, and I've done so in an implicit manner where this UH is chosen to be k plus 1. So this means the time step at k plus 1, or U approximation of U at tk plus 1. Right, so if I'm thinking about it, let's just write it even more generically. UH at time level k. This is an approximation of the true solution at tk. So that's what we're looking at. We're only going to therefore grab little time snapshots. We're going to get one at T1, T2, T3, okay? So T1, T2, T3. Each one of these is going to have a snapshot of the finite element solution as we're progressing along. So this is the Backward-Euler-Galerkin method. The way this practically works is you're given UHK, and from that, you're going to have to solve UHK plus 1. But UHK plus 1 is bound up in this term and this term. Now, this term over here on this side doesn't depend on UHK plus 1. It's based on the weak formulation. In fact, it's based on the semi-discrete formulation above. The test functions are arbitrary elements from the finite element space, and the initial conditions are the same as before. Only you notice that this is the initial approximation UH0. So you actually get something at UH0. And what is that approximation? Well, it's exactly equal to VH, which is the projection of V into VH. Now, using the same sort of analyses that I've done before, I could write these unknowns. That's what I'm looking for, these finite element functions, in this way. So for each finite element function that I'm looking for, I'm going to assume it has this basis expansion. It's expanded in the basis, but I'm going to collect these as my coefficients. Okay, these are the coefficients of this finite element function. Notice that they're not explicitly dependent on time. The time dependence actually comes with this superscript that indicates the time dependence, but they're not functions of time as they were before. So in any case, using the same analysis, we can show that this finite element method we defined here is exactly equivalent to G times UK plus 1. This is the coordinate vector of UHK plus 1 plus S times the stiffness matrix A times the coordinate vector at K plus 1. And that has to be equal to S times FK plus 1 and plus G times UK. Where does this come from? Well, all I do is I'm going to start with this form here, and first thing I'm going to do is multiply through by S. The next thing I'm going to do is I realize I'm going to have a minus UK psi in the L2 norm, and I'm going to move that over to the right-hand side. And the reason why I'm doing that is because this is a known function. What I'm doing is I'm given UK and I'm trying to get UK plus 1. That's how it works. You get K, then you're going to get K plus 1 after that, and then after that K plus 2 and K plus 3 and so on. So you step along in time, you kind of sweep along in time, I guess is another way of putting it. So it's an exercise to show that the finite element method that I described here can be rewritten in matrix vector format, just like this. And this should be this should remind us that this looks a lot like what we had before, but now instead of a time derivative, we just have a time difference. In fact, it's exactly the same as it was above. You can think about simply taking this time derivative here and replace that by the time difference, and you get exactly the same model. It's just not so clear where that would come from. Whereas for doing it this way, it's clear. Let's see. It's clear that this finite element method is based on the weak formulation and just replacing the time derivative by the time difference. All right. So I claim you can convert to that. I'll let you go through those details to do the conversion. So how do we define UK plus 1? What does it mean? Well, it means what you would expect it to mean. UK vector is a coordinate vector of the basis expansion using the standard basis B. And what is F vector F superscript K? By the way, none of these are powers. These are all superscript. So this vector is defined through these coordinates, and the coordinates are given here. And I won't go through all the details of this. It's a fairly simple conversion, and it's left as an exercise to get from, the exercise is going from here to here. And I hope that you can see how to do that after we've done it above. Now, it's very simple then to write an equivalent version of this scheme. And the equivalent version is simply gotten by using the distributive property for these two terms. I'm going to remove the common factor UK plus 1, and then I get a method which looks like this. Now, what is it about this scheme? Well, it's very nice because this scheme has the property that it's going to be an SPD matrix plus S, where S is positive number, times another SPD matrix. If I have that, then I know that this coefficient matrix G plus SA has to be SPD. So this says that this is invertible. So I can multiply, but now this is not the way you do it, but I could, if I had the inverse, multiply both sides by the inverse, and then I would have an explicit formulation or an explicit solution for my UK plus 1 vector. In terms of the previous, well, this is known information always, and this information here is known if I've stepped through in order. So that means I probably should step through in order from k equals 0 up to k equals capital K. That's what I'm going to do. So the next thing I want to show is we showed that the weak solution of the PDE is energy stable. We showed that the semi-discrete Galerkin approximation is stable. And now we're going to show that the Backward-Euler-Galerkin method is also stable in a similar sort of manner. So how are we going to do this? What are we going to be doing? Well, let's start by making some suppositions. Suppose that the projection of V into my finite element mesh, measured in the L2 norm squared actually, is less than the original function V norm in the L2 norm squared, plus a constant. So this is going to be independent of H. And as we said before, we might be able to get away with, instead of C being strictly greater than 0, C greater than or equal to 0. I can tell you in many cases, I can just set this one here equal to 0. What about this one? Maybe not this one. But what is it saying? What is this all saying? Well, I can think about this as being like a Riemann approximation, a Riemann approximation of the integral. Or in other words, this is a Riemann sum, and there's my integral. How close is the Riemann sum to the actual integral? Well, it's off by a little bit. It's off by an error. But the good news about the error is that it never, once I pick my initial mesh, then this is going to get better and better as H and S get smaller and smaller. And so, in fact, in this case, this one is going to get better as S gets smaller and smaller. So I can think about this as being some error between this exact integral and this approximation of it. This is just some measure of the error, the difference. Okay, as long as it's positive and independent of H and S, then I'm good to go. All right, then I can prove that the max of this guy from now, I'm not going to take max over all times because I don't have all times characterized. All I have are time snapshots. K equals 0 all the way up to K equals capital K. But I can still take the maximum of those objects in the L2 norm squared. And the objects I'm going to get over here is now, before it was an integral in time, now I can't get an integral in time. The best I can get is this summation. And so that's fine, as long as what these two things are less than are things which are completely independent of H and S. And through the proof, we're going to find out what this C0 constant should be. In fact, I should write that C0 is, well, greater than or equal to 0. That's fine. This guy is independent of S and H. Now, it's maybe difficult to see that without going through the proof, so let's go through the proof. The easiest thing to do is use 19.5. 19.5 is the definition of the Backward-Euler-Galerkin method using the weak formulation approach. And what I'm going to do is, since I'm allowed to take psi to be any finite element function, I'm going to take that to be equal to UHK plus 1. Okay, UHK plus 1. So let's do that. Substitute in psi equals UHK plus 1. I get that. I get this nice term here. And by the way, I've also multiplied through by S. If you look at 19.5, it has an S in the denominator of a single term. I'm going to multiply through by S everywhere you see. So I lose the that parameter S, which is what we call the step size. I lose that in the denominator of that first term, but I gain it as a factor in each of the other terms. Okay. Right, this is what I have now. I've done nothing except for set the test function equal to this function, the true solution of the scheme at time level K plus 1. This superscript here means the time index. Okay, now I'm going to use something called the polarization identity. This comes up a lot, so it's a good idea to remember it at this point. Polarization identity, and this comes from a very simple identity, actually, that I want to show you. So what is the simple identity? If I just do A minus B quantity times A, then I should be able to show that that's 1/2 A squared minus 1/2 B squared plus 1/2 A minus B squared. So does this work out? Well, you can see that it does work out. Simply multiply A times, well, actually distribute A across this difference. You're going to get what terms? Over here, I'm going to get A squared minus A times B. And then do the same thing on the other side. Multiply out terms. Well, there's only one term that I need to multiply out, and that's this term here. So I get 1/2 A squared. Cross term is going to be minus 2AB multiplied by 1/2, so I get minus AB. And then the last term is going to be plus 1/2 B squared. The 1/2 B squared cancels with the 1/2 B squared. The 1/2 A and the 1/2 A add to give A squared. So I get A squared minus AB. So it checks out. So I'll erase all that work that we did down there. and I'll simply put that the polarization identity above follows from this simple version of the polarization identity. So this polarization identity here follows from that simpler polarization identity. And now I'll let you prove that. That's an exercise. Now, once we have that, I'm going to stick this in this location here. Replace that with that. Okay. So what I get then is if I do this replacement as I indicated into this location, then there's the polarization identity there. There's my second term, and there's the term on the right-hand side. Now the term on the right-hand side, we're going to treat the way we always do. We've done this many, many times. We do Cauchy-Schwarz first, Poincare next. Why Poincare? Because we're going to boost this to the U H K plus 1 H1 semi-norm. Then we're going to use the algebraic geometric mean inequality because we want an S over 2 here, and here we don't care what we get. Okay, before we just had a 1/2 here and a C squared over 1/2 here. Why did I want this term? This term can be hidden. That's the standard way of saying it. This term can be hidden in this term. When I hide it, I'm going to do it by subtracting this term from both sides. So this reduces this to an S over 2 term. Then, like always, I have a term which is, we have a bunch of 1/2s, which I'm going to eliminate by multiplying through by 2. So I do that next, multiply through by 2. But then you'll look at this term and say, yeah, but you've lost a term. What about this term here? What about that term? Well, I'm going to keep it at first. Then I multiply by 2. But then I'm going to throw it away by estimating what remains with something smaller. And the something smaller is just everything except for that term. So basically I can throw that term away. It doesn't supply anything, but it has the right sign. This term being positive is really everything for me in this method. The fact that that term is positive is quite useful. But I'm going to throw it away. Why? It has the right sign that allows me to do so, and that gives me this. The reason why I don't want that one is because it just gives me miscellaneous information that's not going to help me with my ultimate analysis. Now, we can't integrate this in time like we've done before. What are we going to do? We can't integrate, but we can sum. So what I'm going to do is summation is like an integration whenever it's like poor man's integration. If I can't do an integration in time, I still can sum. So we're going to sum this from k equals 0 to k equals L minus 1. And then we're going to realize, well, if I do a summation on terms which look like that, then I'm going to get telescoping. What happens when I telescope is I get intermediate terms are going to cancel. Just try it out. Just try it out. The only thing that's going to survive is the term here associated with the largest index. So it's going to be L minus 1 plus 1. That's just going to be time index L. That's going to be the largest one. And the last one here, well, this guy here is just going to be equal to the first time index associated to k equals 0. Okay, so what I get when I do the sum is I get those two terms only. The intermediate terms all telescope. What about this guy? I can't really do anything with that. I can't really do anything with that, and it just gives me that term that you see there. But I'm going to leave that for now because it looks nice. On the right-hand side, when I sum, I get this. I just get that. All right, now what do I have? This is now my initial condition, right? Because that's how I initialized my scheme. I said that UH0 is equal to VH. This is a plus sign on this side. I'm going to add that term to both sides. that term becomes VH on the right-hand side and it disappears from the left. So now I have these two terms on the left-hand side, right-hand side, these two terms on the left. I'm going to increase this to its maximum possible value. Increase this up to its maximum possible value. Then I'm going to use my assumption. My assumption was that the maximum possible value is going to be L equals capital K. And now I'm going to use my assumption that that is well approximated by the full integral plus some error constant, which is independent of H and S. All right, so I increase this up to capital K. Then I can replace it by an integral plus a constant. It's actually going to be in here, I can replace this part by the integral plus a constant, but then I have a c squared times that constant. That's going to give me c squared times the constant, which I'm just going to call c again. And what about this one? Well, I said that this could be less than, or should be less than v nor L2 norm squared plus another constant. And then I just combine those two constants together. Now, once I get to this spot here, everything that you see over here is completely independent of K, or actually of L. Okay, it's completely independent of that. It doesn't care what this value of L is. Let's see, I have a typo there. Those should be K's. Little k. Only this one should be L. That's correct. Okay. It's a dummy summation inside this as a summand. It carries its superscript as a dummy summation. So it goes from K equals 1 up to capital L. So that's correct. Now, I just do what I've done before. Now this guy is dependent on L. This is completely independent of L. I can take the max on that term. And what should I take the max on? Let's take the maximum of all the possible values that L could possibly be. And what I get is, when I take that maximum, I just get a term which looks like that. Now, you could maximize in K or maximize in L, it doesn't matter. What about this term? This term, I can just take L up to its largest possible value, and that gives me K equals 1 to capital K. And this has to be less than the same set of numbers as well, because this is independent of L over here. This depends on L. Just run this up to its maximum value, and it'll still be true. Maximum value is capital K. And so I get this is also less than these numbers. All right, so these numbers over here, I'm just going to call the constant, let's call it 1/2 C0, 1/2 C0. Well, this is less than 1/2 C0, and this guy is less than 1/2 C0. So add them back together, and you can show that the sum is less than C0. Okay, so that's where that comes from. So now let's review what we've done. We introduced a semi-discrete approximation. We showed that it had a certain type of stability. Now we've introduced the backward-Euler version, and we showed that it too has a useful stability, okay, or it looks like it may be useful. The difference is previously when we had time being a continuous variable, this was a maximum over all possible times. Now it's just a maximum over all possible time indices, but the time indices are discrete. They're discretized. Okay, so I don't know information about the solution or the approximate solution at all times. I can only get approximations at the TKs. Okay, TK where K is equal to 0, 1, 2, up to capital K. Same with this. Previously, for the semi-discrete scheme, this was an integral. Now it's something which looks like what I would call a Riemann sum. We can't get the integral because you can't integrate. There's no there aren't times at each possible time. There's only approximations at certain time steps. And so the next best possible thing that you can get instead of the integral in time is this summation in time, this Riemann sum. In any case, both of these, independent of S and independent of H, are always bounded by a constant. So that says that these quantities can never blow up. Remember what you're going to be doing when you're taking better and better approximations or looking for better and better approximations. You're taking S small and you're taking H small. In fact, you want to think about taking them to all the way to 0. And as I take them to zeros, think about what this guy becomes. As I take S to 0, this is going to start looking more and more like an integral because that's what Riemann sums do. And this guy is going to start looking more and more like a maximum taken over all possible times. Because as I take smaller and smaller time steps, I'm filling in more and more detail, more and more resolution. Okay, so these start to look like the continuous versions. The nice thing is this stability set's kind of like a backstop for me. It says that you can never blow up as H is getting smaller and smaller. That's what we call stability. When you have a numerical scheme that can blow up as H and S get small, then we say that that method is not stable. It's unstable. Okay, and there are plenty of examples of this, and we went through those in Math 572 here at the University of Tennessee. Examples where we were taking smaller and smaller time steps or spatial steps, but the approximation wasn't getting better, it was becoming garbage. And that was because that we don't have a stability available to us. Okay, so with that, I'm going to end this lecture a little bit early, and I can take your questions.